In late 2022, researchers announced a breakthrough experiment in quantum teleportation, sparking widespread attention and even some sensational claims online. A few discussions went as far as suggesting that MIT's mysterious quantum afterimage appeared following a teleportation run. But what exactly does this mean, and what are these so-called quantum teleportation experiments really about? In this video, we'll break it down and answer all your questions. So, let's get started. MIT's wormhole-inspired teleportation simulation. In December 2022, an international team of researchers from the Massachusetts Institute of Technology, the California Institute of Technology, Harvard University, and Google Quantum AI published a landmark paper in Nature that instantly drew global attention. The study was heralded as one of the first practical demonstrations of a phenomenon long confined to the realm of theory: teleportation through a simulated wormhole. This was the first successful transfer of quantum information across an engineered system that behaved mathematically like a traversable wormhole. This breakthrough marked a crucial intersection of quantum information science and theoretical physics, bringing concepts from Einstein's theory of general relativity and string theory into contact with laboratory results for the first time. Caltech and Harvard contributed their deep theoretical expertise in high-energy physics and the mathematical framework of holography, while MIT provided quantum information theorists and computational modeling expertise. Google Quantum AI brought to the table its powerful Sycamore quantum processor, which had already been used in 2019 to demonstrate a form of quantum supremacy by performing a calculation that would have taken classical supercomputers thousands of years. The blending of these distinct strengths created the perfect environment for testing ideas that had previously only been explored on paper. So, how big of a deal is it, really? Well, it's huge. The Nature paper was formally titled Traversable Wormhole Dynamics on a Quantum Processor, and it represented the culmination of years of effort to bring holographic duality, a central concept in modern theoretical physics, into contact with real quantum systems. The principle underlying this work is the antide sitter conformal field theory correspondence, better known as ADS-CFT, first proposed by physicist Juan Maldacena in 1997 at Princeton's Institute for Advanced Study. Maldacena's insight was that certain strongly interacting quantum systems can be equivalently described as gravitational systems in a curved higher-dimensional space. In other words, phenomena that appear as black holes or wormholes in one description can be reformulated as interactions between particles in a lower-dimensional quantum field theory. This duality has been one of the most influential ideas in physics over the last quarter-century, and the MIT Caltech-Harvard-Google collaboration sought to give it experimental form. The experimental setup was intricate. Instead of attempting to create an actual wormhole, a structure that would require exotic matter with negative energy density and is not known to exist in the physical universe, the team built a quantum circuit that could mimic the mathematics of wormhole traversal. The system was constructed on Google's Sycamore quantum processor, which is a superconducting device with dozens of qubits cooled to near absolute zero. Qubits, the quantum equivalent of classical bits, can exist in superpositions of states and can be entangled with one another, meaning their properties are correlated across distance in ways that defy classical expectations. For the experiment, the team designed two entangled sets of qubits that served as the two ends of a simulated wormhole. Once the entangled systems were established, the researchers followed a carefully designed protocol. They inserted a qubit of information into one side of the entangled system. To simulate the conditions of a traversable wormhole, they applied a sequence of engineered interactions that the team referred to as a shockwave. This shockwave was not a physical disturbance but a controlled manipulation of the system's Hamiltonian, the operator that defines the energy and dynamics of a quantum system. The result of this manipulation was that the quantum information injected into one side of the system emerged on the other side, in a manner consistent with what one would expect if it had passed through a wormhole. One of the most important aspects of this result is what did not happen. The transmission of quantum information did not occur faster than light, nor did it involve the transport of mass or energy. The signal moved within the strict limits of causality set by both quantum mechanics and special relativity. In fact, the classical communication channel required to complete the teleportation protocol still enforced that nothing could happen in a way that violated Einstein's cosmic speed limit. This ensured that the experiment, while exotic in its design, remained firmly consistent with the laws of physics as they are currently understood. The successful demonstration had enormous implications. First, it showed that wormhole-like behavior could be recreated in a laboratory setting using existing quantum technology. This does not mean that scientists are on the brink of creating real wormholes that people or spacecraft can travel through, but it does mean that some of the most challenging and abstract ideas in theoretical physics can now be probed through direct experiments. Second, the result provided an important proof of concept for the link between quantum entanglement and the geometry of spacetime. Physicists such as Leonard Susskind at Stanford and Juan Maldacena have argued for years that entanglement is the glue that holds spacetime together, with wormholes representing a geometric manifestation of entangled states. The MIT-led team's experiment gave the first tangible evidence that such an interpretation can be mapped onto working quantum devices. The use of Sycamore's quantum processor was crucial in making this possible. Unlike classical computers, which would require astronomical resources to simulate entangled systems of this complexity, Sycamore could directly implement the quantum circuits needed to test the wormhole protocol. The processor used in this experiment did not employ its full complement of qubits, but rather a tailored subset configured specifically for the test. By fine-tuning the interactions, the team was able to compress the dynamics of a complex many-body system into a manageable number of qubits while still preserving the essential mathematical structure. Such is the direction of modern physics.